welcome to another algebra lesson. We are on 6.2, properties of rational exponents and radicals. So let's jump in here, face out of the way. So properties of rational exponents and radicals. So by the end of this, you'll be able to simplify and rewrite expressions containing rational exponents and nth roots. So here's our Spark Gear Learning, Part A. So the manufacturing company makes 4 different size cylindrical cans. The volume doubles for each increase in size. The 4 sizes have volumes of that, and that. Although the cans being manufactured in different sizes, they are the same shape. The height of each can is twice its radius. So we've got a variety of equations that we can set up. So, mathematical questions. What are the heights? What are the radiuses? The radius is going to help determine these tracks, how big those tracks need to be, / what their machinery needs to be set at. Like the height would have to change. So these are all good mathematical questions that we can ask, we can talk about. So they of course gave us the volume, and so they've got a surface area equation right here. And as you can see, it kind of looks a little hairy, right? So you've got a cubed root, a squared, and so solving that would be a little bit challenging unless you knew all of the exponent rules that we're about to go over. So let's just jump right into the lesson and let's get started. So our first task here, to build our understanding, investigate the properties of rational exponents. So we previously used properties to simplify and evaluate expressions with integer exponents. Some examples are shown. So this is kind of what we did in our last lesson. Well, no, I'm sorry. In our last lesson, we were doing cubed roots and fractional exponents. But this is something that hopefully you've seen before. I know for a fact if you are in my chemistry class, you've seen this before. But a way of working with exponents is, so if you take this one, for example, so they've got 3 squared multiplied by 3 cubed. And so if you add those 2 exponents up together, you've got 3 to the 5th, which then equals your final answer. So you can do that with any exponent, which is what we're about to find out. So a similar rule. So we've got multiplication right here. So if you were doing division, so 3 squared divided by 3 to the 3rd is equal to 2 minus 3, which is equal to 3 to the negative 1. So this is where things get a little weird, but shouldn't be too bad. So when you have a negative 1 in an exponent, so that's basically like 1 over 3. So like your negative 2 would be 1 over 3 squared and things like that. So that negative sign just essentially turns it into an inverse. So then right here, if you look at this one right there, so if you bring a power to another power, instead of adding those like you would at this top part, you're going to multiply them together. So that's going to equal 3 to the power of 6. And then we've seen this one before using the square roots. So 3 over 4 squared is the same as 3 squared over 4 squared. Okay, so then they are, of course, going to ask, hey, we have a pattern here. Let's hear. Click to reveal general rules that apply to integer exponents. So you can actually expand these rules to any integer exponents. So this is basically right here what we're doing in this lesson. So if you can remember those, and in my opinion, they're not terribly hard to remember, but you just have to remember these four, one, two, three, four, yeah, five things, then you're good to go, to be completely honest. So let's see what they got for us. Apply one of the general rules to each expression on the left to help you simplify the one of the results on the right. So, okay. This is multiplied together, so you can just add them. So, boop, there you go. That's 1/2 right there plus 3/4. So this is divided by, so you're just going to subtract them. Is that the right one? 9/4 minus, yep. These are the power brought to another power, so you're going to multiply them. And the product rule, you can split this up like that. And then this guy, you can again split that up like that. Yay, nice work. So show that 81 to the power of 1/2 times 81 to the power of 3/4 and 81 to the power of 5/4 have the same value when simplified. So are they wanting us to, yeah, so it looks like we're going to simplify this guy, simplify this guy, multiply them together, and then simplify this guy. May need a calculator for some of this. So 81 to the 1/2 power is the same as the square root of 81. 9 times 9 is 81. 81, let's see if I can do this all without a calculator, to the 3/4 is equal to the 4th root of 81 cubed. Actually, we're going to put that cube on the outside. We're going to do that second. Cube. Remember, from our last lesson, we are able to do that. So we know that the square root is 9. The square root of that 9 is 3. So it's going to be 3 cubed. 3 times 3 is 9, times 3 is 27. So then we multiply those together. I lost my calculator, so I guess I'm not using a calculator. So when we multiply those together, you're going to get, what is that? 27 times 9 is equal to 243. So then this part, we can just shove this part into our calculator. Oh no, that's not what they want us to do. So we're going to divide this up into our cubed root and then our 5th. So remember our 4th root of 81 is 3. 3 to the power of 5 is 243. Good thinking. So based on your results for part B, predict the rule for the product of powers property for rational exponents. Didn't we already go over that? Whatever. So since they're being products, it doesn't matter whether it's a fraction or not. It's the same thing. You're just going to add those together. Does your work in part B prove the product power? the product of powers property for rational exponents? If not, what must be done to prove the property? Product of powers property. I would say it mostly proves it. Typically proofs you don't use real numbers in, so you have to find some way to represent all possible numbers. So you would have to figure out a way to represent all like negative integers and things like that. But it does show that our product power does work. So we're going to leave it at that. Based on your evaluation of that and 81 there, predict the rule for power. So again, when it's a power brought to the power, you're just going to multiply those together. So that's like that. All right, we got a couple more examples coming up. So simplify expressions involving rational exponents. So here we have everything we need to know. Again, this is basically the entire lesson right here. So if you can do this part, you're good to go. So, and this one also labels each property. So that's never something that I will tend to test you on. But if you ever needed to like do a proof or anything like that, you would have to use the product of powers property, the quotient of powers property, things like that. And I'm sure that the book is going to have us do those things as well, but that's okay. So here's your examples. I'm not going to go through all those. Here's your algebra version, and let's move forward. So it says simplify the expression of that. So it's divided by, so based on, looks like this one, quotient of powers property, you're going to subtract them. So 5 over 2 minus 6 over 2. And so we said the quotient power of properties. This is all a matter of me spelling it correctly. Quotient. I probably spelled it wrong, didn't I? Well, anyway. Not this one. Take a deep breath and try again. They're so positive. So anyway, as we simplify, so we're still in that same problem. We've got, so as we simplify, so once we have this part right here, it becomes just a normal fractional problem. Remember, when you're doing fractions, you first have to have a common denominator. So here we do, and that's 2. So then you can just subtract the top. So that's 5 minus 6. So you're going to have a negative 1/2 left over. So that's where they got this part right here. Remember, I mentioned when you have a negative exponent, it just goes down into the denominator and it becomes positive, and then you just simplify from there. 25, or the square root of 25 is 5, and so our answer is 1/5. Too easy, right? Definition of a rational root? Sure, why not? Nope. Of a negative power. I didn't see that one. That's no fair. Whatever. Yeah, so the definition of a negative power is what makes you do that. All right, let's take it a step further and let's start doing actual algebra as opposed to regular math. Because algebra, we have letters. So we're going to throw some variables in here and see how everything works. So it gives us simplify the expression. Come on, zoom in. You can do it. There it is. Simplify the expression, this whole mess. So yes, it looks messy, and I would not want to try to solve that myself. But using those properties, we can then make it into something that's not terrible. So let's start inside of the parenthesis. We should always start inside of the parenthesis. So we have just this part. That's a y to the power of 3/4 over an 8y to the power of -1/2. So our definition of negative power. See, yeah, they're even being goofy. You would never see a negative power in a denominator. That's kind of dumb. But anyway, so the negative power only goes with the y. So that's why they brought it up here. So now we've got our y to the power of 3/4. We're right here. So another way to have done this, you could actually have skipped this step and just stuck with your quotient rule and said, so that would equal y 3/4 minus a -1/2. And then that would end up, adding, which is the same thing that's going to happen here. So either way that you think about it works, it doesn't matter. So yeah, that's what they did here. They're adding their fractions together now because it was a product. They needed to find, so they had to add 3/4 plus 1/2. So 1/2 is equal to 2/4, so that we have that common denominator. So then we have 5/4 is what that turns into. So that's where we get our 5/4. And it's still raised to 2/3. So because of our raise to the power rule, so we're just going to take this one, raise it to a power, and this one, raise it to a power. This is a number, so we can just shove that into our calculator if we wanted to come up with a number. This is a power rule, so we're not going to add those, we're going to multiply them together. And so when we multiply, fractions, that's whenever you just multiply straight across. So 5 times 2 is 10, 4 times 3 is 6, 12, and then you simplify. So let's see, 5/6. I pulled a 2 out. And then there you go. So they either shoved this in a calculator or they just knew the cubed root of 8 is 2. Think about it. 2 times 2 is 4 times 2 is 8. And then they raised the 2 to the second power, which then equals 4. So that equals 4, which is where they got this fraction. So this is one of the parts where I love math. We took this horrible, horrible looking mess, and really that entire thing is just this little guy. That's all it is. Right? Too easy. I say that in jest. I know that this is challenging sometimes. So match each property with the rewritten expression that it justifies. See, this is the part where I'm really bad. Power of a power property They're taking a power of a power, right? Product of powers, right there. And then what's left over, let's see. Ah! Oh, yeah. I'm sorry. I'm crazy. Let me try again. Power of a power, that's when you multiply them together. So see right here, they're multiplying those together, turns into that. That was my bad. Power of a quotient, I wouldn't, I don't know, I wouldn't call it power of a quotient, but whatever. There you go. So again, these are being able to correctly identify which property it is less important to me as being able to actually do it. This would become important if you, for some odd reason, get into high math academia and start coming up with proofs and things like that. Got one more extension of this, maybe one, I don't know. But we're going to do more algebra. And algebra is so cool. So simplify radical expressions involving nth roots. So now we're putting our variable into the power part of the function. So this is something that we've done before using the square roots and or the product roots property and quotient roots property. But you can also do that with letters. So things like, the fourth root of 48 is also equal to the fourth root of 16 times the fourth root of 3. So then the fourth root of 16 is 2. So this is something that hopefully you have seen before. But you can do the same thing with letters. Okay? And then also with quotients, again, the same thing. You can split that up. So looks like they have a little proof for us. The product of roots. Let's zoom in. So we start off with the nth root of AB. We can raise the whole thing to 1 over n. That's the same thing. So then using our our product properties, we can split that up, and then we can turn it back into the nth root. So, and then this is kind of sort of the same thing. I'm not going to go through it all with you. So an example, though, would be simplify the expression cubed root of 64 over y squared. So we start with our given. We can do the cubed root of 64 over the cubed root of y squared. So the cubed root of 64, I'm just going to cheat. I'm going to look here, is 4. I saw it right there. So then we can make that top part, just call it 4. And then that bottom part, we can actually change that to y 2 over 3, right? Ooh, but they don't like rational, or they don't like irrational things in the denominator. So this would be wrong. We don't want you to do that. So here we go. We've got, where were we? Cube root with y squared underneath. So to rationalize, you're going to times both top and bottom, well, you're going to times your fraction by a really fancy version of 1, where cube root of y over cube root of y. Wait, that doesn't work. Oh, I get what they're doing. So I'm looking right here, and I was wondering what they were doing, because I thought I was going to cancel out. That's not going to. What it does is, so we get cube root of y, 4 cube root of y on top, and then we have the cube root of y cubed, because we multiplied it by another one. So this, having the square here, is the same as saying cube root of y times cube root of y times cube root of y. So now we have the cube root of y cubed, which simplifies to just y. So if this was just the cube root of y, we would then have to multiply it by the cube root of y squared so that our two numbers matched. So then on top, we still have 4 cube root of y. So we don't like icky numbers in the denominator, aka irrational numbers in the denominator. We like rational and happy numbers. Oh, this is the part that I'm the worst at, remembering these products. Match each property with the rewritten expression that it justifies. So this seems like quotient, because they're dividing stuff. And property of roots. Oh, whew, I did get that wrong. Right. You know I'm not good at that. Hey, so you made it. That's the end of our lesson. As is your tradition, hopefully, you will have a check on learning. Try it out first, and then if you don't like it, watch the next video. I'll see you then.